Hey guys, today we're going to be talking about solving limits algebraically. First of all, what is a limit? A limit is the value that a function approaches but never quite reaches that value. So it gets closer and closer, but it never quite gets there. Well, what does a limit help us solve? Limits help us solve continuity, derivatives, and integrals, but we're not going to get into that today. Today, we are going to go over how to solve a limit with direct substitution, or a limit with undefined denominators. We'll also touch the squeeze theorem, and I'll also talk about special limits today. Do not forget, limits are the fundamental steps of calculus. Now we're going to look at solving limits with direct substitution. Direct substitution means as x is approaching a number, we are going to then put that number into the problem where there is an x and try and solve the problem. For example, we are going to look at the limit as x approaches 2 of 2x squared plus 5x minus 6. We are going to plug this 2 into every place that there is an x. So now we're looking at 2 times 2 squared plus 5 times 2 minus 6. 2 squared is 4. Multiply that by the 2 out front. Plus 5 times 2 is 10 minus 6. 2 times 4 is 8. Carry this down, plus 10 minus 6. So now we've got 18 minus 6. So that means the limit for this problem is 12. Next, let's look at a limit that has a numerator and a denominator. So the limit is x approaches 4 of x squared minus 25 over x plus 4. The first step that you want to take is make sure that this number plugged into the denominator doesn't give you 0. If it gives you 0, we've got a problem. So let's start plugging 4 into this problem. We have 4 squared minus 25 over 4 plus 4. Well, 4 squared is 16 minus 25 over 8. 16 minus 25 is going to give you a negative 9, and then you have this denominator. So then therefore, as the limit of x approaches 4 of x squared minus 25 over x plus 4 is negative 9 over 8. Now we're going to look at solving limits with 0 in the denominator. So what happens when we try to plug in as the x value approaches into the denominator that ultimately gives us 0? So here we're looking at the limit as x approaches 3 of x squared minus x minus 6 over x minus 3. The first step is to use direct substitution if we can. As x approaches 3, we're going to plug this 3 into the denominator first, as I said earlier. Well, 3 minus 3 gives you 0, which you can't do because that gives you an undefined. So that means we have to manipulate the problem a little bit. Let's look at our numerator. We have x squared minus x minus 6. Immediately, hopefully we can notice that this is a polynomial that can be factored out. So x squared minus x minus 6 is going to be x minus 3 times x plus 2. You FOIL this out and it will give you x squared minus x minus 6. You put that all under x minus 3. Now you can see that we have like terms on the numerator and the denominator, which will cancel out. So now we're left with just the x plus 2. So as the limit of x approaches 3 of x plus 2, we then can use direct substitution from this 3 into the x. So then we have 3 plus 2. 3 plus 2 is 5. And that will be the answer for this problem. Now we're going to look at solving limits using the squeeze theorem. This is g of x is lesser or equal than f of x, which is lesser or equal than h of x. So the first step is to solve the limit of g of x, which goes as follows. The limit as x approaches a number of g of x will give you an answer, which is represented by the letter L. And then you need to find the limit of h of x, which is limit as x approaches a number of h of x gives you the same number represented by L. Therefore, if g of x is L and h of x is L, therefore you know the limit as x approaches a of f of x must be L. I'm taking it, that was fine. Now that we know how to use the squeeze theorem, let's use it in an example. For example, the limit as x approaches 0 of x squared sine 1 over x. Now we know sine is between negative 1 and positive 1 whenever you graph sine, so we're going to put negative x as our g of x and positive x as our h of x, and regular sine 1 over x as our f of x because there's only one x. Now, as you can see, we have to have x squared in our problem to get the correct answer. So we multiply everything by 2. So we have negative x squared, which is lesser than equal than x squared sine over 1 of x, which is lesser or equal than x squared. Now, to solve using the squeeze theorem, you must take the limit of g of x and the limit of h of x, and if those numbers that you get as a limit as the answer is the same answer, then therefore you know that f of x is the same answer as well. So the limit of x approaches 0 of negative x squared, which is our g of x, is 0, negative 0 squared, which is just 0. Now looking at h of x, limit as x approaches 0 of x squared, 0 squared is still just 0. Therefore, 0 equals 0, 0. Therefore, the limit as x approaches 0 of x squared sine 1 over x, f of x is also 0. Now we'll look at solving special limits or trigonomic limits. These limits are the limit as x approaches 0 of sine of x over x equals 1, the limit of x approaches 0 of 1 minus cos x over x is 0, and the limit of x approaches 0 of 1 plus x to the 1 over x power equals e, or Euler's number. For this example, we're just going to be looking at the first special limit of sine. So if we have the example, limit as x approaches 0 of cos x times tan x over x, we know that we can separate this problem as cos x over x multiplied by tan x. Now tan x, as we know, can be represented as sine of x over cos of x. So then we have the limit as x approaches 0 of cos x over x multiplied by sine x over cos x. As you can see, we have some like terms of cos x here on the top and the bottom, so these terms can cancel out. So what we're left with is the limit as x approaches 0 of sine x over x, which we know from the first special limit is 1. And now we know how to solve limits.